questions from homework? I know Boyd has already told me he's got some to talk about. What you want to start with, Boyd?
Can we start with 19?
Sure. So it says 2 concentric circles are cut by the same angle. All right, let's start there. Who remembers what concentric means from geometry?
Like they're kind of like one that's inside the other one.
Excellent. Yeah, they share the same center, so it kind of looks like a bullseye. So I'll draw something like this. Pardon my bad circling. Yeah, just means they share the same center, so like it's a bullseye. One's inside of the other. Olivia?
This is the chapter 1 review, right?
This is chapter 2 problems. No problem. Super clear, or super okay to ask, even though it says chapter 2 problems right at the top that we're looking at. That's okay. I'm just giving you a hard time now. If I can't tease a kid every once in a while. No. What part when does chapter 2 stuff do?
The end of the semester.
Close. Let's double check the.
Next Sunday, because the reviews do this.
Yeah, the reviews due Sunday. I think the chapter 2 stuff let's make due next week. Everybody's cool with that? Shh. All right. Stop talking, please. Let's now that we got all that straightened out, let's get back to this. It says the radius of the smaller circle is 4.3. So those sections are 4.3. And it says, and the cut arc measures 5.2. Okay. The radius of the larger circle is 5.2. What is the length of the cut arc? Everybody's okay with what we've drawn there, picture-wise? Just based on the words that it said? Okay, the arc length formula, and I'm going to call this I'm going to call these radius for the bigger one R2. I'm going to call that arc length S2. I'll call this arc length S1, and I'll call these radiuses R1 for the shorter circle, just so it's a little bit easier to communicate what part I'm talking about. Is that okay with you guys? Okay, the 1s are for the little one and the 2s are for the big one. All right, so I know that S2 is equal to R2 times theta, and the key observation here is that that theta is going to be the same theta for the little circle and the big circle, right? Now the problem here appears to be that the only thing I have is my value for R2. I don't have a value for theta. However, if I look at the little circle, I do have 2 of the 3 values there. So if I divide both sides by 4.3, I can get my value for theta there. Does this feel okay so far, Boyd?
Yeah.
Okay. If you did not, holler at me or whatever, and we can be more specific, or I can elaborate or whatever, but trying to go slowly and explain what's going on. And since that is the same theta, for both of these. I can just plug that in. I get about 6.29. I think all of the units here were measured in inches, so that should be in inches. Does that feel okay?
So that's the answer.
That's the answer, 6.29. Yep. Hopefully that wasn't as bad as it seemed initially. Getting a good accurate picture drawn was pretty key to seeing how to do that though, right? If I didn't have that picture, it was going to be pretty rough to make that observation that like, hey, it's the same theta for both of these situations, which was the key to being able to do that. Did you have another one you want to talk about?
We talk about 22.
Sure. Oh, same kind of problem. Two toy racetracks form concentric circles. Okay. So we've already talked about what that means. Each racetrack is divided into 15 identical sections. Okay. So I'm just going to draw one of those 15 identical sections. Call it that. And it says if the inside car travels 1.2 centimeters less than the outside car on each piece of track, so if this is S1 and this is S2, S1 is equal to S2 minus 1.2. That's what that sentence was saying, right? If the inside car travels 1.2 centimeters less than the outer car on each piece of track, how much bigger is the radius of the outside track than the radius of, compared to the radius of the inside track? Okay. Says set up two equations using the arc length formula and use substitution to solve. God bless you. Okay, so far so good. Thank you. All right, here's the problem though, right? We don't know what theta is. We're actually told how to find this though. What part of our problem tells us how to find that theta? Boyd? Yeah, the 15 identical sections. So how many radians are in one circle? So that we have 360 degrees in one circle, right? And we remember that our conversion factor was 180 degrees is equal to pi radians. So how many radians must I have in a 360? 2 pi, right? Everybody agree with that? That if 1 pi is 180 degrees, 2 pi has to be 360 degrees, right? That should be clear, right? Now, could you use degrees here instead of radians? Yeah. What's the downside of doing that, though? These formulas are get a little bit more irritating to deal with, right? So I'm gonna use radians. So if I take that 2 pi then, and I divide it by 15, that has to be the angle measure for theta. Since I'm just taking the whole circle and dividing it into 15 pizza slices, each pizza slice must be 1/15 of the whole. The whole was 360 or 2 pi, then the slice was 2 pi over 15. All right. So now what I'm going to do, I'm going to make this substitution. I'm going to say that S2 is equal to R2 times 2 pi over 15. And then S2 minus 1.2 is equal to R1 times 2 pi over 15. Everybody okay with that? Is that okay? Everybody's all right? All right. So this is my system that I'm going to solve. It suggests I use substitution to do that. Okay. So what I'm going to do is I'm going to use the first equation, which tells me that S2 is this, and I'm going to substitute it in for the S2 in the second equation. So that's going to give me R2 times 2 pi over 15 minus 1.2 is equal to R1 times 2 pi over 15. Everybody's good with that? I'm going to subtract the R1 times 2 pi theta from both sides. And at the same time, I'm going to add the 1.2 to both sides. So I can get the variables on one side and my constant on the other. So far, so good. If I look at that left-hand side, I notice that both of these have a factor of 2 pi over 15. So I can factor that off. And then to get that out of there, to get the 2 pi over 15 to the other side, what did I do?
Divide.
You could divide by the fraction, or what's equivalent to dividing by a fraction?
Multiply by the
Yeah, multiplying by the reciprocal. Inverse is okay to say too. And that's the way I'm going to think about it. Um, 15 times 1.2 and then divide by 2, 11.25. Well, let's just do, and then divide by pi. Just do it all at once. So I have 3.58. Does that answer the question? Well, let's read it again. So it says, the thing that you should be suspicious about is that, like, Mr. Kulik, you still have two variables here, right? I have R2 and R1. But let's read the question again. It says, how much bigger is the radius of the outside track compared to the inside track? If I were to compare their sizes, what operation would you do to find out how much bigger something is? Subtract. R2 is the outside, and R1 is the inside. That's exactly what we've solved for here, was how much bigger the radius of the outside track was then the radius of the inside track. Woof, Mr. Kulik. In the picture, where is this 3.58 really talking about? Talking about that piece right there. Just to connect it to like the picture back again, right? That was a toughie. The algebra got a little bit tricky in there, particularly knowing that R2 minus R1 was going to be your answer. Maybe we should have started by explaining that rather than going. Yeah. You live and you learn, right? Okay. Others from this section? Boyd.
24.
All right, 24. There's a unit conversion problem. It says a circular saw has a diameter of 8.25 inches, and there's 12 inches or 12 teeth per inch on the cutting blade. If the saw spins at 3,500 revolutions per minute, how many cutting teeth cross the surface each second? So this is going to be a unit conversion problem. What I read here is this is like a rate. Well, I would say this this is a conversion factor, right? So I'd say I know that 12 teeth equals 1 inch. And I know that the diameter is 8.25 inches. And I want to convert 3,500 revolutions per minute into teeth per second. Everybody okay with that explanation, or that setup anyways? So first thing I know or notice is that, well, I'm starting in per minute. I want to end in per second. So let's start first by converting minutes to seconds. Since minutes is in the denominator of my fraction, where does minutes have to appear in my next fraction? The top, right? And I know 1 minute is 60 seconds. So if I do that, I'm left with per seconds. Everybody's cool with that? Next thing I need to do is I need to figure out a way to convert revolutions into teeth. Well, I know that I can convert teeth or linear distance into teeth because I have this conversion factor. What I need to do now is somehow convert revolutions into a linear distance. And we talked about this in the notes in the example, that 1 revolution is equal to 1 circumference. Which in our case is, since we're talking about a circular saw blade, is 2 pi r. And what's the r here? It's the diameter divided by 2. Everybody's okay with that? So, since I have revolutions on top in my fraction, I know that I need revolutions on bottom. And my conversion factor here says that 1 revolution is 8.25 pi inches. And then my next conversion factor tells me that 1 inch is 12 teeth. So when I multiply through, revolutions cancel, inches cancel, and I'm left with teeth per second. Righteous, Mr. Hulick. All I need to do now is to type this into my calculator. I'm going to use the fraction command on this so I don't have to worry about my parentheses. And I know when I multiply fractions, I just multiply straight across. And I don't have to worry about the ones, because the ones when I multiply don't do anything. They don't do nothing. So when I do that, I get 18,142.7. It's a lot of teeth. It's a heck of a saw blade. Meow. That's what it sounds like when you're using a power saw. I thought it would help connect it to the real world. If you're like, oh, I just cut off my finger. My father did that when he was a young man. Well, just the tips of these two fingers. No, he just doesn't have the tip of two fingers. Using a table saw, like holding the board and just... I mean, it looks, not really. I mean, one finger doesn't really have a fingernail on it. Because that's how much got chopped off. So be careful using power tools. After that grisly story, who else has any more questions? Lucas. 26? Did we get to 26? I thought I asked you to stop at 24. Yeah, we shouldn't have done 26 yet. So I'm going to table that because that content we'll talk about in today. So if you didn't know how to do that one, that was okay. You shouldn't have, because we haven't talked about it yet. Boy, did you have one?
Yeah, one more. 23.
23. Okay. So this one is almost going to be identical to what we did in the notes. Right? Just instead of a car, this is a bicycle, right? So it's, again, this is a unit conversion problem. It's like almost identical to the last example in the notes. Stop talking for me. So remember that in our notes, the car had 18-inch diameter tires. It seems like a small car tire, going 15 miles an hour, and asks how many revolutions per second the tires were making. In this question, we have a bicycle with 22-inch diameter wheels going 14 miles per hour, and we're asking how many revolutions per minute the tires are making. Almost the exact same question, right? So what we did in 24 is going to be almost the exact same work. The only difference is that instead of going to revolutions per second, we're going to be going to per minute. So, I guess first things first, I'll start by converting hours into minutes. 1 hour is not 1 minute. That would be some weird time dilation going on. So there's that. And then somehow I got to convert miles into revolutions. Well, we did that last time, right? In the notes. Again, the key is that one circumference is 1 revolution. And how big were these tires? 22 inches. So the radius is 11. So 22 pi inches is my circumference. I just have to convert miles into inches before I can use that conversion factor. So I know 1 mile is 5,280 feet. You're welcome, dude. And then I know that 1 foot is 12 inches. And I know then that 22 pi inches is 1 revolution. So if I do that, miles will cancel with miles, feet with feet, inches with inches, and we're left with revolutions per minute. And now it's just to gotta multiply it out, right? Can I leave that part for you guys? Once we've done the setup, the multiplication, the calculator is probably pretty easy. And since it's an odd one, you have the answer in the back, which I think will be good to just make sure you can get it in your calculator correctly to check on that. You know what I mean? Thanks, dude. All right, my friends. Let's start section 2 of old chapter 2 here. Okie dokie. All right. Let's do it, my vegetable people. So in section 2.2, we're going to go back in time and do some trig functions on acute or with acute angles. So this is like what we would have done in geometry. So if I'm looking at a right triangle, and I'm looking at this angle theta that I've drawn in, this side in yellow I would call opposite, adjacent, or hypotenuse.
Adjacent.
Good. And then this side in green would be opposite. And this side in blue, hypotenuse. So if we remember SOHCAHTOA, I know that sine theta is opposite over hypotenuse. I know that cosine theta is adjacent over hypotenuse. And I know that tan theta is opposite over adjacent. Everybody's okay with that? Are those the only 3 ratios I could write with opposite, adjacent, hypotenuse? Why couldn't I have written hypotenuse over opposite? Like, why did I choose these 3? Those are just what you were told, because guess what? There are 3 more. Yeah, you do.
What are these ones called?
Are they just like, they're just reversed?
Oh, opposites.
Yeah. You'd say reciprocal is usually the word. So let's give these guys a name. Hypotenuse over opposite we're going to call cosecant theta. Okay. Hypotenuse over adjacent we're going to call secant theta. And then adjacent over opposite we're going to call cotangent theta. So we actually are going to have 6 trig ratios that we'll use. But Mr. Kulik, how am I supposed to remember these other 6 now? Here's how you remember. 1, these are just reciprocals of the other ones, right? So which pair of reciprocals are going to be the easiest to remember just based on the names? Tangent and cotangent, right? Everybody agree with that? That'll be easy to remember that cotangent's just a reciprocal. How am I going to keep cosecant and secant straight? No cos go together. So cosine does not go with cosecant. It goes with secant. And then it's just a reciprocal. Sine goes with cosecant. They're just reciprocals. So that's what I would encourage you guys in terms of remembering these three new ones, is that we're not memorizing three new things. You're just remembering that they're reciprocals and then which ones pair with which, right? Tangent with cotangent, sine with secant, sine with cosecant, and then cosine with secant, right? Just like the way I've written them together here. That's the easier way to remember that. Everybody cool? Okay. Let's do a quickie example of just kind of using these in a really basic sense. Yes. Cosecant. So just CO and then secant, just like the other one. We'll show you in a moment. Okay. Example says to write all 6 ratios for this, well, I should say for theta. And then we give you this triangle with theta in it. First thing should strike you when you look at this triangle. What are you missing? One of the side lengths, right? Exactly. And this side length in this case is the hypotenuse. So before we can start writing these ratios, what are we going to have to find? The hypotenuse. How do we do that? Excellent. We can use the Pythagorean theorem. What's the thing we have to be careful about when using the Pythagorean theorem? The hypotenuse must be C. Does it matter whether 2 goes with A or with B? It does not. The legs do not matter. So I get that the square root of 29 is my hypotenuse. Everybody cool with what we did there? Okay. All right, let's start writing these guys down then. Sine theta, what would I write? Five over the square root of 29, right? Do you suppose that's the best way to write that? What don't we like about this? The square root in the denominator. How do we get rid of it? Multiply the top and bottom by the square root of 29. Oh my goodness. Everybody feel good there? Cosine theta, what's that going to be? 2 over square root of 29. We're going to have to do the same thing. I'm not going to show the step there. Is that okay with everybody? That I just wrote the answer? Everybody's cool that it's the same step in there. They didn't need to write that. If you're not, I can go back and elaborate, but I feel like we should be good. We good? Okay. Tan theta is 5/2. All right. Cosecant theta. Who's saying, Mr. Kulik, can we scroll over to look at the triangle again? I'd be like, nah, don't do that. What do we remember? What is cosecant the reciprocal of? Sine, which we already did. Yeah, not sin. We're not in religion class. So I'll just write the reciprocal, right? Once I've done sine, cosine, and tangent, I'm not going to go back and look at the triangle again to do cosecant, secant, and cotangent. I'm just going to look at the reciprocals, right? Isn't that easier? Notice what part did I look at? The part that I didn't rationalize, right? I'm looking at the original ratio because I don't want to have to re-rationalize it and then reduce. So I'm not looking at my final answer for sine. I'm looking at the very first thing that I wrote down. We cool? Okay, what's cosine or secant going to be? Square root 29/2. And cotangent? 2/5. Mr. Kulik. That was pretty fast. That was pretty easy. Even though these are new and kind of weird. Once I had sine, cosine, and tangent, they're a piece of cake to deal with. Right? I just have to remember which one is the reciprocal of which one. No big deal. Everybody's cool? So far, so good? All right, let's do another example. Yeah, we just wanted to write the 6 ratios. We wrote the 6 ratios. Right? I guess I didn't box them. I don't know why I didn't stop boxing. All right. It says let theta be an acute angle of a right triangle. If sine is equal to 1/3, find the other 5 trig ratios. First thing I would start by doing is making a picture. My picture should specifically be a right triangle. Right? So I'm going to draw theta in as one of the acute angles. Everybody's cool with that? Now, somehow, the other piece of information I'm given is that sine of theta equals 1/3. I'm going to use that to start trying to label the side lengths in my triangle. What does sine theta equals 1/3 allow me to label? Opposite, which should be 1, and the hypotenuse, which should be 3. How am I going to find that third side? Pythagorean theorem. So what do I write here for the Pythagorean theorem? Very good. Again, we had to be careful there that we made sure that the hypotenuse was our C in the Pythagorean theorem. Yeah. Can we do better than the square root of 8, though? Do you remember how you simplify radicals? So can I rewrite 8 as the product of a perfect square and another number? 4 and 2, right? So I could think about this as the square root of 4 times the square root of 2. And I know the square root of 4 is just 2, and I still have the times 2. Everybody good? All right. So let's start writing our other 5 ratios. Okay. Which one do you want to start with? Cosine. All right. What's cosine? 2 root 2 over 3. Looks good. What do you want to do next? Tangent. Okay. What's tangent? Okay. Do I like the way that looks? What do I need to do to it? I'm just going to multiply by root 2 over root 2. I don't need to do the 2 root 2 to the top and bottom and leave myself enough space here. So when I multiply root 2 times root 2, what do I get? Root 4, which is the same thing as 2. So this will become square root 2 over 4. Pretty cool there. Okay, cosecant. What's that going to be? 3. Which is the same thing as 3, right? 3 over 1. How did you do that so fast? It's just the reciprocal of sine, right? Don't need the triangle. Once we have sine, cosine, and tangent, I can get the other 3 by just looking at reciprocals. You could use the triangle also. It's fine, but like, save yourself the aggravation, right? Secant should be, 3 over 2 square root 2, which again, we'd have to rationalize those denominators. I'm going to skip showing the work there on that step. Is that okay with you guys? It's like the same work as before, but. And then cotangent. Yeah, just 2 square root 2. Nice. Basically the same problem as before, right? We just had the one extra step of having to like find those 2 sides of the triangle initially from the trig ratio. But that's fine. That wasn't a big deal. I think you guys knew immediately what to do with it, right? So that's good. Okay. Okay. What if we ask you to find sine of 30 degrees without your calculator? No, how dare you, sir? How in the world am I supposed to do that, Mr. Kulik? Okay. Sure, let's start by building out a right triangle. One of the angles has to be 30. What is it, Boyd?
So 30 plus 90 plus blank equals 180.
Yes. So blank is
It's 60. Yeah.
60 degrees. Great. Does that start ringing any bells? Back to geometry. There are two special right triangles you would have talked about in geometry, the 30, 60, 90 triangle and the 45, 45, 90 triangle. The 30, 60, 90 triangle has ratios of side lengths of x as the short side, x root 3 as the long side, and then, or I said the short leg, the longer leg, and then 2x is the hypotenuse. Does that ring a bell? The way to remember this, which one goes where, the way I remember this anyways, is that the shortest side should be across from the shortest angle. The middle side should be across from the middle angle, and the biggest side should be across from the biggest angle. And you should say, Mr. Kulik, how do I know whether like 2 or square root 3 is bigger? Well, just type square root 3 in your calculator. It's like 179, right? 2 is bigger than 179, which is bigger than 1. So like you can tell immediately like which of those is the biggest. Or sometimes I hear people say that like, I know that the 3's go next to each other. So like the 30 degree and the square root 3 go right next to each other like that. That's fine too. Most people get the hypotenuse in the right place. Everybody cool with that? So sine of 30 degrees then should be 1x over 2x, or reducing down to just 1/2. Woo! So this guy is one that is a good one to remember. That comes up a fair bit. The other one that we talked about was the 45, 45, 90 triangle. Let's write that one in real quick because, again, it's been a few minutes since we've had a geometry class. And I know all that stuff fades. So the ratio of side lengths for a 45, 45, 90 triangle, the legs are both x, since it's an isosceles triangle, and the hypotenuse is x root 2. Figure, since we're on the topic, we might as well review that real quick too. Okay, what if I ask you to find sine of 17 degrees? Notice there's no special direction on this, right? So we have to calculator it up. Okay? Before I start typing this into my calculator, what should I check? That my calculator is in the correct mode. This problem says sine of 17 degrees. What mode should my calculator be in? Degree mode. So to check that, I'm going to press the mode button that's right here next to the blue second. And then make sure I'm in degree mode, which I wasn't. So I've just moved my down and pressed enter on the degree. To get back out, I'll press second and mode. And then I can just type it in exactly as it looks, sine of 17. So I get about 0.292.
I think the test should just be those.
Yeah? What if I wanted secant of 78 degrees? Now, if I look at my calculator, do I see a secant button on here anywhere?
No, but there's sine inverse.
Well, sine inverse is a different function. That's not the same as the reciprocal. That's why I've cautioned you guys against using inverse and reciprocal interchangeably. So sine inverse isn't the same thing as the reciprocal of sine. Oh no. So sine, cosine, tangent, which one is secant related to? Cosine. And it's related to it as it's the reciprocal, right? So I'm just going to type it in as 1 over cosine 78. So I get about 4810. Alpha y equals, and then the first option. We've been talking about that since like day one. Olivia. How else could I type this into my calculator? You could type it like this, right, with the division symbol. Or you could even do cosine 78, and then you can do this button, the -1 exponent. Any of those are fine. They all do the exact same thing. So again, depending on your calculator's operating system, like Boyd over here doesn't have the fancy type fractions on his. Those other two options, though, are perfect, will work for you right away, though. All right. Okay. Last example here before we move on to the next section.
Just banging up the sections. Hanging them up.
Well, the next section is quite brief, but quite important conceptually. So I like having about 20 minutes to kind of do that. That should be good to do. All right, solve the triangle. What does that mean when the directions say solve the triangle? All the side lengths and all the angle measures, right? Okay, what do you want to find first? Okay, sure. So what am I going to use to find, I'll call this side x then. You can find it. So relative to this angle, the side we know is adjacent. The side we want is hypotenuse. So the trig function I'll use is cosine, because cosine is adjacent over hypotenuse. Everybody okay with that? To solve for x, I'm going to multiply both sides by x to get it out of the denominator. And then divide both sides by cosine of 41 degrees. And then it's just calculator time. So about 15.90. Okay. What side do you want to get next? Or what part do you want to get next? I guess we have a side and an angle.
I'm feeling the angle of
Okay, how do we do that? I'll call that y for the record. Okay, so I know 180 degrees is equal to y plus 41 plus 90. So what do we get there? 49 is y. Okay, so we got one piece left. I guess we'll call that part z. How am I going to find z? So I think Emma's saying that considering the 41, we know the adjacent, and we're looking for the opposite, so we could use tangent, would be what I would use. I'd probably stay away from secant, cosecant, cotangent on these kinds of problems, because none of those buttons are on my calculator. I could use them, but it's not making my life any easier to do that. So I would probably just stay away. I'll multiply both sides by 12 to get the z by itself, and then it's just calculator time. So I get 1043 or thereabouts. Is that fruit fly or something? I blame the biology department.
I blame the school.
Oh,
The entire school, but
okay, thanks. All right, so that's it for section 2. Relatively easy skills. These are all geometry review skills, things you would have done in geometry, aside from the 3 new trig ratios, but like that wasn't a big deal, right? Didn't turn out to really make life any more difficult. Okay. 2.3, we're going to change gears and return to our conversation about angles. So in geometry, when I drew an angle like this, we're always talking about like that angle measure, right? Everybody agree with that?
You don't have one?
But what would stop us from instead wanting to talk about that angle?
well, 2.3 is here.
Right? That seems like a valid, still seems like something we might want to do. Everybody agree? So we're going to find a new way to describe an angle and a new way to measure the measure of an angle. Or I'm not to measure, but to describe the measures of angles. So when we do this, we would call this arm of our angle the initial side. Because when I drew my little arrows there, they're starting from that side of that arm of my angle. Does everybody kind of see that? This arm of my angle, where my arrows stop, we would call the terminal side. Everybody's okay there? So what I'm going to do now is I'm going to imagine for any angle measure, I can embed that onto the XY axis. And I can always place the initial side on the positive x-axis. And then I can imagine the terminal side starting at the positive x-axis and rotating around the xy axis. Right? So something like that. What's the huge advantage of thinking about angles this way? Is that now we can represent things, angles that are bigger than 180 degrees, right? In geometry, we couldn't draw angles like that. Now we can. Now notice in both of these drawings, I drew my angles counterclockwise. Why couldn't I have drawn them just regular clockwise? Well, there's no reason I couldn't, so we're going to take advantage of that ability to rotate either direction. Our counterclockwise rotation, we're going to use for positive angles. And the clockwise rotation is going to represent negative angles. Yes, Sophie? Sure. So just pause for a second and think about what we've just done. In geometry, the angle measures we're able to represent were stuck between 0 and 180. Everybody agree with that? I now can rotate bigger than 180, and I can go negative. I have negative angles now possible because I've defined things this way. I can now represent a negative angle. I can represent angles bigger than 180. And in fact, imagine that I wanted to represent angles bigger than 360. What would that look like? So let's say like I wanted to represent a 540 degree angle. Skateboarders and snowboarders, what's a 540?
360.
So 1.5 rotations, right? So if I start at my initial side, I would go 1 full time around and then a half a time around. And that would be a 540 degree angle, right? Where I've done 1.5 rotations and I went counterclockwise because I represented this as a positive angle. So now not only can I represent angles bigger than 180, can I make my angles big as I want? Yeah. I now have a way to define angles of any size from negative infinity to positive infinity. It's very cool, right? That's a big change from geometry. Now, I want to point out something else to you. In doing this, what if I wanted to graph a 180 degree angle on the same axes here? So again, initial side, 180 degrees, terminal side. What do you notice about the 540 angle and the 180 degree angle? The initial side and the terminal side are in the exact same locations. Everybody see that? We're going to give that kind of an angle a special name. We're going to call these kinds of angles coterminal angles. So these are angles with different measurements. but identical terminal sides. All right, let's do a quick example to practice these finding coterminal angles. So it says find two angles coterminal of 47 degrees. Okay, so if I draw a 47-degree angle, initial side always on the positive x-axis. Terminal side is around here. Everybody okay with that? Okay. So one way I could draw a coterminal angle to this is I start at the same initial side. I go one full time around and then 47 more. How much would that be in blue? Well, it'd be 360 for the full rotation, and then 47 degrees for to get back to the terminal side in the same location. So 407. Everybody okay with that? If I want to find another one, what can I do? Well, what if I start again at the same initial side and I do one time around and then two times around and then end up back at the same terminal side? So I did 360 for once around, 360 for the second time around, and then the 47 to get back to the same spot. So I would have said 767. Are these the only two coterminal angles I could have found? No, I could keep on going, right? And doing 3 rotations, 4 rotations, 5 rotations, etc. Or what else could I have done? Could have gone backwards, right? By doing a backwards rotation, negative 360. Etc., right? Do you notice? Oh, I wrote the wrong number there. That's a 7. Do you notice anything between these numbers, or any pattern between these two numbers, or 3 numbers, I should say? Just adding 360. Well, I was just thinking we're just adding 360 each time. So how can I, if I didn't want to draw the picture like we did, how can I generate coterminal angles? Just keep adding or subtracting 360 and it'll keep giving you coterminal angles. Whoa! That's pretty nice, Mr. Kula, because that drawing you had down there got kind of messy. Well, it's no big deal. What if instead of an angle in degrees, we gave you an angle in radians? Oh no! Don't fear, it's not a big deal. What are we going to be? So just before, when he did the problems that Boyd was asking about, how many radians was 360 degrees the same as? 2 pi. You remember that? We talked about that when we were doing the homework problems. So guess what? Instead of adding 360, I'm going to be adding 2 pi. Okay? And can I do pi over 3 plus 2 pi in my calculator and get an exact answer? Nope. What am I going to have to do to add those two things together? Make a common denominator. That common denominator would be 3. So that would be 7 pi over 3. Everybody's okay with that? And then to find my next coterminal angle, well, I'm going to just add 2 pi to the answer from my previous one, make my common denominator. There's a second. Everybody cool? Now, if you're like Mr. Kulik, I despise fractions. Is there a way for me to do this still on my calculator? Here's what you can do. So I can do this same problem on my calculator if I leave the pi's out, do the arithmetic on my calculator, and then put the pi's back in at the end. So if I do 1/3 instead of pi over 3, plus 2 instead of plus 2 pi, and then I press the math button and pick the fraction command, it'll give me, okay, that's 7/3, and then I just stick the pi back in at the end myself manually. Is everybody okay with that? That'll save you from the hassle of like adding and subtracting fractions a trillion times. You can use your calculator to do that arithmetic, but you can't put the pi's in to do it. The reason is pi is an irrational number, so as soon as that goes in there, your calculator is not going to return you a fraction if you have a pi in there. So you have to leave those off, do the arithmetic, and then write the pi back in yourself. Remember to write the pi back in yourself at the end. But that feels pretty good for today. Is that okay with you guys? Nothing too bonkers we did there. The good news is that you guys should be able to do up to 44 now. Again, that's going to go not into this Sunday's homework set, but the next Sunday's, along with the 1 through 24. All right.